So now we've got another one of our sponsors. Is it Midonet or Midcura?
Company is Midcura. The product is Midonet.
Okay, so talking about software-defined networking, we have Tomohiko. Loves a bit of salsa dancing. Used to work on some cool search stuff at Google, and now most recently is working on software-defined networking and visualization around Elasticsearch. So be doing a bit of a case study review around some OpenStack software-defined networking with Ceph underneath.
Yeah, so I'm going to talk about our experiences and what we learned through this PoC stuff. Anyway, thank you for everyone. I guess you guys must be tired by now, but I hope, okay. Yeah, I'm a software engineer for Midokura, developing a network virtualization agent. And so, but I'm just a software engineer. I'm not even network guy. I'm not even, storage guy. So don't ask me any hard questions. Otherwise, I have to pass it on to Andrew sitting there. So he's my buddy. So anyway, so I'm going to talk about this PoC stuff where we try to basically abstract everything, compute, storage, and network. And anyway, this is a typical, a large academic research lab in Europe. And the environment is pretty proprietary. So they have proprietary high-end server machine, network gears, and a lot of complex configurations. Because of that, so whenever a new project comes up, then the first thing they have to do is ask for more storage and ask for new servers, custom configuration, write papers, ask for permission and stuff. And a lot of that's developmental bureaucracy and overhead. So basically, they wanted to streamline the development process. So I don't know if they want to abstract data center itself, but basically they want abstract, like I said, compute and storage and network, and put another abstraction layer on top of it, and do some, cool intelligent monitoring, and basically manage all the resources under one umbrella. And of course, so in order to move from more like waterfall or agile developmental, development paradigm to more like, recent, like DevOps kind of style, so that they can quickly, prototype stuff and put it, send it to the production. And of course, they want to do it, of course, the other requirements, like, they want balance load across the different data centers. And of course, everything needs to be scalable, but, I guess there are two ways to scale. I guess one is scale up and another is scale out. Scale up means like, I guess, paying more for servers and paying more for network gears, paying, proprietary stuff and stuff. But on the other hand, scale out, you just add, cheap white box gears and add more servers, add more stuff, and, that's another way of scaling out. Then basically our goal is to allow the environment, the system, network to be scalable in the sense that it can scale out easily. And of course, they want isolation for the security reason. Tenant shouldn't interact with other tenants. So, and of course, they want advanced management capability, like recent trend like big data stuff. They want analytics, features, like they want track of how many flows are being created each second, and going where to there, and maybe doing into the detection stuff. So that's our the goal of this PoC. So the use case is, in short, it's an OpenStack Newton, production grade deployment. And basically, software-defined networking is all about, the separation of control plane from the data plane. And of course, they want the cool management capability that provided by Horizon for topology management and deployment. And of course, the Midonet provides routing protocols and gateway and BGP stuff, and say VXLAN stuff. And also for the network and management purpose, we have a flow tracing feature where you can simulate the flow on the fly from the horizon control panel and to see why the packet it doesn't reach the target VM and stuff. So those are the for us the use cases for this particular PoC. Anyway, so to do software-defined everything, we decided to use MiddleNet for network, and Ceph, of course, for storage, and Red Hat for OpenStack management platform. Integration platform. And the last one, I guess it's called hardware management and monitoring. They use XCAT or something like that. So it's typically there are more OpenStacky solutions like Puppets and Ansible, but these customers not just want to manage their storage and network, but they also manage, or they want to be able to do upgrade, firmware upgrade. So and this tool can do that. So that's why they decided to use this. So, by the way, so yeah, just to explain the picture. So those lower stacks are for the Ceph, and in the middle, the servers for the OpenStack controllers, and the above are for the compute. Anyway, I'm switching my slide to hope. Sorry. So I'm going to talk a little bit about software-defined networking, so that we can. So the purpose of software-defined networking is basically, decoupling control from the data plane, so that you can manage the network configuration at the central location. You don't have to go each routers and network boxes to do manual configuration and stuff. So then it has to be agile. It has to be scalable. And so instead of proprietary hardware, this software-defined networking allows you to use cheap white box gears, so that it can easily scale out by adding more and more cheaper gears. So then here comes OpenStack Neutron. So OpenStack Neutron is a project in OpenStack, as most of you know. So it defines the Northbound API for the network management layer. So and it provides the southbound vendor plugins. So historically, Neutron was a part of Nova. It's an OpenStack compute project, and so which was first introduced in 2010. And it's in a monolithic, so they didn't think that network needs to be independent project. So the feature is limited, only L2 per DHCP. But I guess it was stable. It is stable, and it did what it's supposed to do. So there are still many customers and clients that still stick to Nova. So then Neutron spawned out of Nova, and at the sixth release of Folsom. So it's more. So it now has a decoupled network API, and it's so basically API driven and scalable. So it has a default implementation based on Open vSwitch. So the problem with Open vSwitch is So design is still design model is centralized control, so that instead of distributed management. So basically, Open vSwitch becomes a bottleneck, a traffic bottleneck, and also it's a single point of failure. And so every packet, in order to be handled, needs to go through this central node. That means that there is a traffic trombone. And on the other hand, MiddleNet is it's also a OpenStack Neutron plugin. So its design is basically MiddleNet is a network overlay solution. So basically, all we need is a L3 connectivity in underlying, physical network. Then so we build the virtual network is an overlay on top of a physical network, and so it's just unlike Open vSwitch default neutron plugin implementation, so which is centralized. Our model is a distributed control. So all the computations are done at the edge on each VM host, meaning that single VM or hypervisor may go down, but there is no single point of failure. So it's more fault tolerant, and it's more it can easily scale out because if we want to scale out, like I said, you just add servers and add connect it to the network and just run the agent. Midnet agent on this server. So and yeah, like I said, all the networks. So network simulations for the virtual network is done at the edge at each closest server. So that what single virtual hop means. So you don't have to. Packets don't need to go to the central control node. So that way its latency is also low. Yeah, I think I talked about this. Yeah, and also there are some more advanced features like L3 and L3 gateways. Oh my gosh. Yeah, and we also have BGP border nodes. And also we have a VTEP capability. So if necessary, we can do Midnet can do VXLAN offload using multiple hardware VXLAN tunnel endpoints. So I guess I don't think you can see the details, but it's just an image of what overlay means. So we have below we have a physical network, that provides L3 connectivity. And on top of that, the agent runs on each supervisor and VM sits inside. But those are mapped to virtual port in the physical layer. And those physical virtual switches and routers are created by, created through Neutron API. And so on this side, there's a uplink. So there's a BGP gateway is there sitting at the servers connected to the uplinks and out to the internet. So anyway, so like I said, and firewall is also provided by the by software, and its firewall functionality is provided at the supervisor, so it doesn't. If the malicious packets come, it doesn't reach the physical network at all. So that's another feature. And because Docker is everywhere and it's fashionable, now we can handle Docker too. And so Midnet itself provides Puppet and Ansible modules for easy installation management. And we open sourced it last year around this time. So it's 1 year old after it became open sourced. And more. Sorry. And switch back to So anyway, so that's the this description of Midnet technology and what it does, how it's used and stuff. And this is Ceph architecture, which I guess all of you are pretty much familiar, so I'm not going into details. And that's the stuff that they used for management. So extreme cloud administration tool called XCAT and open source, and so it can do firmware updates and stuff. So and design. So basically it's the same thing. So because we don't need that expensive hardware, we just need leaf and spine, ECMP, like silos, layout, which is, and like I said, I think I didn't explain, but so yeah, so when packet comes in, so I said that computation is done at the edge. So the packet comes in, then flow for miss, there's a if there's a cache miss, the flow is not in the obvious, DB kernel module table, then it's there's a net link upcall to the midnet agent, which does all the simulations and computes flow to install the flow. And basically, then midnet agent establishes a GRE tunnel between the target host and source host, and that's all the actual packets are sent to those GRE. And only the first packets may require some simulation, but from the second one, it doesn't add much overhead. So it's an image like this. So I guess there's a darker shade is the virtual machine, whereas the lighter shade is physical node. So like gateway host is on top. Anyway, it's not going to. So I guess quickly I go over the hardware. So we deployed 4 controller nodes, a CPU, 2 sockets into Haswell, and memory is 64 gigabytes, storage 4 times 4 terabyte hardware, and 8 Ceph OSD nodes, CPU, one socket Intel Haswell, and memory is 64 gigabyte and 8 times 8 terabyte hard disk OSD, 20 gigabyte SSD for channeling, and 16 compute nodes, CPU is 2 sockets Intel Haswell, 20 cores, and memory was 384 gigabytes, and all nodes. So these are the hardwares. And so basically just what kind of technology we used. So as OpenStack, So for compute, of course, Nova. For storage, of course, Ceph for Cinder and Glance, and networking is done by Newton plugin. Midnet Newton plugin. Of course, the identity is served by Keystone, and we use the Horizon as a dashboard. We also used accelerometer and heat for monitoring and orchestration, just to show that we can do it, but we didn't do much actual work into those. So configurations basically default configuration mostly. But we needed some dedicated links for BGP gateways. I think I forgot the number, but then, and we did a lot of tuning using BGP timers. But we figured out that it needs to be BGP timers needed to be shortened for the quicker failovers when the link fails. And also, large receive offloads needs to be turned off for gateway nodes because some technical issues, and agent basically didn't send packets that's not larger than the target VM's MTU. So, and we need the port groups for gateways, and also, I guess it's with hindsight it's common sense, but we needed to client Zookeeper connections because basically we use Zookeeper as configuration or topology management, and as I guess basically the Zookeeper needs a connection as many as 8 number of agents, I think. And for the Ceph configuration, ref replication factor is 3, and 64 OSD spread equally between 8 nodes, and SSD to HD hard disk drive ratio is 1:4. If I understand correctly, I guess it's not really typical. I guess typical is 1:5, but we use 1:4. We saw some performance improvement, but not as much as. And based on these numbers, we calculated the placement groups numbers, which is 4,096. And also, we used 2 10 gig NICs, and we aggregated it, and we put 2 trunks, one for VLAN and one for cluster network for segregation of network. And so lessons learned. I guess it's a common sense. I guess you should plan out before you do plan out. You should plan well. Seems like because with the software-defined everything, seems like small thing can be easily changed afterwards, but that's not actually the case. So like the number of MPUs and IP address assignments and stuff, because so we misconfigured the size of the MTU. Then we needed to make it smaller because of the issue that I think I just talked about it. Then RabbitMQ started acting strangely, and RabbitMQ in particular was a nightmare for this experience, for this POC. And restarting RabbitMQ is not as easy as it may sound, so because it just sometimes doesn't comply. So anyway, so But other than that, the rest of the OpenStack components worked seamlessly. And midnet gateway failover was impressive. And then Horizon, I guess it's also a default UI control panel, but limited in functionality and usability. So it shows each device, bridges and networks, but then it also shows features, but all it shows is the UUID and didn't put enough information in a single place, so it lacks usability. So it's not a good, administrator-friendly tool. So, but on the other hand, flow tracing made the debugging easier, because I guess one of the complaints or fear against SDN is that too much abstraction might make it hard to debug. But then now you can do the simulation from the GUI and to see where the packets are being dropped and stuff. So it's now now you have the tool to debug for virtualizations. And so OpenStack related stuff, split planes. So there was issue with the MongoDB stuff. So we had 4 even numbered MongoDB instances. Then there was split plane stuff. So, and also the same for Zookeeper that Middlenet uses. So we recommend odd number of instances for the quorum reason. And restarting RabbitMQ is not a simple task, and power outage can really happen in practice. So don't think that's a theoretical threat. And some minor issues. VXLAN offload only works on a single UDP. And so manual deployment is still complex process. So we write some installers, but I guess there's some way to go. And for the Ceph, I guess most of these are familiar to you. So throughput, I guess reads are always faster than writes, and sometimes five times faster. And IOPS, I guess it's faster. It was quite well even on the spinning drive, and enterprise ready, and even more faster with SSD. At least it doubles. And so if you don't have SSD, we recommend that you plan well about how to partition your network and stuff. I guess so like I said, we used 2 10 gig NICs to introduce trunks, but then I guess it's concur with the previous presentation, but so most of the time network is bottom out and maxed out, and so I guess in short 20 gig NICs is not enough for networks. And I guess another thing, so, and SSD to HDD ratio, so we used the not conventional ratio of 1:4. I guess so I guess it doesn't improve performance as much as the number, but it improves the longevity. So if the ratio for the SSD is too small, SSD tend to wear off pretty quickly. So I guess it also depends on the type of SSD. I guess if it's an enterprise-ready SSD, I guess it's a bit different. But anyway, so as a result, I guess the workflow has been streamlined. So before, I guess, I don't know the details of what it's supposed to mean, but I guess 3 teams had to, the same thing, things need to go back and forth between 3 teams. But after that, then, pretty much straight, And of course, it realized some, business benefits like, all those stuff like rapid deployment and reduced cost and better maintainability and simplified and more manageable network. And because of that, the faster deployment results in more productivity and faster product release, and perfect for the company, I guess. I guess this pretty much covers what I wanted to say. So if there are any questions, I'm happy to answer as long as I can answer them. Thanks.
So that white paper actually goes into significant detail around the entire environment, if anyone wanted to dig into the deployment and the configuration. So take a quick snapshot. Any other questions? I think it's pretty cool. The use of Ceph is not just storage. It supports a whole heap of different use cases. You heard from Blair and Steve earlier, and now supporting software-defined networking. There's a lot of NFV stuff that's happening within the OpenStack and community, and then having Ceph underlying that as well. So it's a very flexible storage system. It's almost like a unicorn if I was to be biased about something. Yes.
Did the Docker containers get their own virtual core?
Oh yeah, that's basically the idea.
So each container had their own core, there wasn't a separate?
Yeah. So basically, container is handled like a virtual machine. So assign the virtual port.
Cool. Any other questions? Cool. Thank you.
Thank you.
Awesome. So we've now got the... Oh, yes, absolutely. Round of applause. We now have the QA roundtable.